Welcome to my online course in linear algebra. Linear algebra is in our fourth semester syllabus. Today's topic of discussion is subspaces of vector space. First is definition of subspaces. Let V be a vector space. A non-empty subset W of P is said to be subspace of P if W itself is a vector space over the field F under the same operation as in P. Next is example of subspaces. First is 0 and P are trivial subspaces of the vector space PF. Q over Q is a subspace of R over Q. Here Q is the set of rational. Set of rational is a vector space over itself. R, the set of real, is a vector space over the field Q. Here Q is a subset of R. So Q over Q is a subspace of R over Q. But Q over Q is not a subspace of R over R, although Q is a subset of R, but here the field of both the vector space are different. The first vector space, the field is Q, and the second vector space, the field is R. So Q over Q is not a subspace of the vector space R over R. Next is theorem on subspace. The necessary and sufficient condition for a non-empty subset W of a vector space BF is a subspace if alpha beta belongs to F, xy belongs to W, implies alpha x plus beta y belongs to W. First, we consider W to be a vector space, W to be a subspace of a vector space P. Then we shall show that this condition holds in W. As W is a subspace of P, W is closed under scalar multiplication. Alpha beta belongs to F, x comma y belongs to W, alpha x comma beta y belongs to W. Again, W is closed under vector addition, so alpha x plus beta y belongs to W. So, if we consider W is a subspace of vector space P, then we have shown that alpha beta belongs to F, xy belongs to W implies alpha x plus beta y belongs to W. That is my first part is proof. Next is only if portion. This is if portion, this is only if portion. So conversely, we consider W to be a non-empty subset of vector space P over the field F such that the following condition holds in W. That is alpha beta belongs to F, xy belongs to W, alpha x plus beta y belongs to W. Next, we shall show that W is a vector space over F. Applying the given condition for alpha beta equal to 1, xy belongs to W, we get 1x plus 1y, that is x plus y belongs to W, that is W is closed under vector addition. Next, applying the given condition, this condition for alpha beta equal to 0, we will get alpha 0, beta 0, and for any x, y, we will get 0 into x plus 0 into y belongs to W. This implies 0x, 0x, 0x. By using properties of vector, I will get 0. Again, for this, I will get 0. Then 0 plus 0 will give you 0. That belongs to W. That means 0 element of P belongs to 0, belongs to W. And also it acts as additive identity of W. For any x belongs to W, alpha is equal to -1 and beta is equal to 0. Then -1 x plus 0 y belongs to W, minus x belongs to W. For any x belongs to W, we take alpha -1 beta equal to 0. By putting this in the given condition, we will get minus x belongs to W. That means its additive inverse of any element of W belongs to W. Further, element of W are element of P. Therefore, addition in W is associative as well as commutative. As they are associative and commutative in P, therefore the W plus is an additive abelian group. If alpha belongs to F and X belongs to W, then we have by the given condition alpha x 0 x belongs to w. Beta equal, here I am putting beta equal to 0. Then I will get alpha x belongs to w. That means alpha w is closed under scalar multiplication. Here you should remove the dots. This is alpha x, alpha x, alpha x. Okay, that is alpha x belongs to w. W is closed under scalar multiplications. Finally, the rest four conditions for a subset to be a vector space holds good in W, as element of W are element of V, and V is a vector space, so rest four condition hold good in W. And therefore, the W is a vector space over the field F. Consequently, W is a subspace of V. Next is example of subspace. Consider R3R. Here our vector spaces R3R, W with a set of all tuples of the form this x1, x2, x3, which satisfy this condition a1, x1 plus a2, x2 plus a3, x3 equal to 0. a1, a2, a3 belongs to W. This shows that W is a subspace of the vector space R3R. Consider 0, 0, 0 belongs to this is R3 such that a1 0 plus a2 0 plus a3 0 is equal to 0. That means 0, 0 belongs to W vector. W, this collection W, therefore W is non-empty. If it is empty, then we can directly say that this is a subspace of R3. As it is not empty, so we have to show that W is a subspace of the vector space R3R, for which we consider two elements x, y, x equal to x1, x2, x3 and y equal to y1, y2, y3 belongs to W, and alpha, beta belong any two elements of the field R. If if x equal to x1, x2, x3 belongs to W, then any element of W will satisfy this condition. So this will be equal to 0. That is a1, x1 plus a2, x2 plus a3, x3 equal to 0, and y equal to y1, y2 plus y1, y2, y3 belongs to W. Then this condition is equal to 0. a1, y1 plus a2, y2 plus a3, y3 is equal to 0. Now alpha x plus beta y will be alpha of x1, x2, x3 plus beta y1, y2, y3. Then it will be alpha x1, alpha x2, alpha x3 plus beta y1, beta y2, beta y3. Then the sum will be the element wise sum, alpha x1 plus alpha y1, and remaining two elements can be obtained similarly. Now a1, now we are going to check out this condition. That is, I am taking a1 with the first element, add up with the a2 multiplied with the second element of alpha x plus beta y, plus a3 multiplied with the third element of the alpha x plus beta y. Then using the properties of vector space, I am getting this one, a1 alpha x1 plus a1 beta y1 plus remaining two element in the term in the bracket can be obtained like this, like the first element. In the next step, we can rearrange the term like this. That is, here it is a1 alpha x1. In the next step, I am writing it alpha a1 x1 by using the properties of vector space plus beta a1 y1. Similarly, I can write the remaining two terms. Now I am writing alpha terms with the alpha terms and taking alpha common, then it will be alpha a1 x1 plus alpha a2 x2 plus a3 x3 plus beta into a1 y1 plus a2 y2 plus a3 y3. This is equal to alpha 0 plus beta 0. Here this is equal to 0 using this value. So alpha 0 plus beta 0, using the properties of vector space, this is equal to 0 plus this is 0. This is equal to 0. Therefore, I can get this alpha x plus beta y is equal to 0, as element will satisfy this condition. This sum is my equal to 0. So alpha x plus beta y belongs to W. Hence, W is a subspace of the vector space R3 over R. Second example, consider Rn over R, W to be the collections of all n tuples of the form x1, x2 up to xn. X1 square is equal to x2. Check whether W is a subspace of the vector space Rn R. Solution, we take alpha equal to 3 and x equal to tuple whose element are 2 except the second element which is 4. Then we check out the scalar multiplications of alpha x, that is 3, with the tuple whose all elements are 2 except the second element which is 4. That is equal to the tuple whose all elements are 6 except the second element which is 12. That does not belong to 12 because this is since 6 square is equal to 36, which does not equal to 12. Therefore, W is not closed under scalar multiplication and hence W is not a vector space and consequently W is not a subspace over Rn R. Next, these are the questions for your practice. You should solve this question. In case of any problem, you can consult me. I will help you in solving these questions. Next is a theorem on subspaces. First theorem is intersection of two subspaces of a vector space is again a subspace of the vector space. Consider W1 and W2 be two subspaces of a vector space over the field F. To show W1 intersection W2 is a subspace of V. Zero element of V belongs to both W1 and W2 as W1 and W2 are subspace of the vector space V. So 0 of V belongs to both W1 and W2. Consequently, the 0 belongs to their intersection and intersection is not empty. So if intersection is not empty, we will proceed with the proof. That is, we consider alpha beta belongs to F, xy belongs to their intersection, then xy belongs to W1, xy belongs to W2. Since W1 is a subspace of the vector space P, alpha beta belongs to F, xy belongs to W1, implies alpha x plus beta y belongs to W1 and alpha beta belongs to F, x, y belongs to W2 implies alpha x plus beta y belongs to W2. This is from the necessary and sufficient condition for a non-empty subset to be a vector space theorem. I am getting this result. Alpha x plus beta y belongs to both W1 and W2. So they belong, alpha x plus beta y belongs to W1 intersection W2. That means W1 intersection W2 is my subspace. However, the converse is not true. That is, union of two, here it is subspace, okay, not vector space. Union of two subspace of a vector space is again a subspace. Consider the vector space R2R and the collection W1 collection of all pairs of the form A, 0, A belongs to the field, and W2 collections of the all element of the form 0, B, where B belongs to R. Then W1 and W2 are subspace of the vector space B2R also represented by R2R is represented by B2R. Now consider their union. W1 union W2 will be the collection of all elements of the form A, 0 and 0, A, where AB belongs to her. In particular, if we take a pair, two pairs, 2, 0, 0, 3 belongs to W1 union W2, then 2, 0 plus 0, 3 equal to 2, 3 does not belongs to W1 union W2. That is, W1 union W2 is not a subspace of the vector space B2R. Next is union of two subspace of a vector space is a subspace if and only if one is contained in the other. In the last theorem, we have seen that intersection of two vector subspace is again a subspace, but union is not not a subspace. Here in this theorem we are going to prove that union of two subspace is a subspace if and only if one is contained in other or other is contained in one. For that we consider W1, W2 be two subspaces of a vector space BF. First, we consider one is contained in other. That is, either W1 is contained in W2 or W2 is contained in W1. Then W1 union W2 will be either any one of W1 or W2. In any case, if W1 union W2 is either W1 or W2, in any case, W1 union W2 is a subspace of the vector space P. Conversely, we consider W1 union W2 be a subspace of P. To show W1 is contained in W2 or W2 is contained in W1. This is or. Suppose W1 is not contained in W2 and this is M. This two you should correct it. To show W1 contained in W2 or W2 contained in W1, for which we will prove it by contradiction method. That is, first we make a suppose. We suppose that W1 is not contained in W2 and W2 not contained in W1. Since W1 is not contained in W2, so there exists X belongs to W1 such that X does not belong to W2. As W1 is not contained in W2, so I will get at least one X that belongs to W1 but does not belong to W2. Again, W2 is not contained in W1, so I will get at least one Y that belongs to W2 but it does not belong to W1. Otherwise, one is contained in other. Here we have considered no one is contained in other. Now, this X belongs to W1, Y belongs to W2. That means X comma Y belongs to their union. As here we consider their union is a subspace. So this W1 union W2 is a subspace. XY belongs to W1 union W2. So X plus Y belongs to W1 union W2. As X plus Y belongs to W1 union W2, X plus Y belongs to W1 or X plus Y belongs to W2. If X plus Y belongs to W1, here we have seen X belongs to W1. From here X plus Y belongs to W1 and from this X belongs to W1. So X plus Y minus X. If X belongs to W1, then additive inverse minus X belongs to W1. As W1 itself is a vector space. As it is a W1 is a subspace, that means it is a vector space. So if X belongs to W1, then its additive inverse belongs to W1. So X plus Y plus minus X belongs to W1. That is W1 is closed under vector addition. So X plus Y minus X, that is Y belongs to W1. Here we have considered an element X belongs to W1. As W1 is not contained in W2, X belongs to W1 but X does not belong to W2. So if X belongs to Y, then since Y belongs to W2, so and W2 is a subspace, so minus Y belongs to W2. Therefore, X plus Y minus Y, that is belongs to W2. Because W2 is closed under vector addition. This is an element belongs to W. This is an element belongs to W. Then its additive inverse belongs to W. Its additive inverse taken sum with this element that belongs to W2. This is due to vector. W2 is closed under vector addition. This implies X belongs to W2. So, which is again a contradiction. This contradiction arises because we have taken W1 is not contained in W2 and W2 not contained in W1. As the proof, last theorem, arbitrary intersection of subspace of a vector space is again a subspace. This is your home assignment. You should try to solve this one. If you get to the proof, then it is nice. If you are unable to solve this one, then you should inform me. I will solve it. Remaining will be in the next lecture. With that, I would like to conclude. Thank you.